Well, hello, boys and girls. Welcome to the first day of the rest of your lives. Everything up to this point, all the friendships, all the learning means nothing because now you are in calculus. I'm going to create a video series going over the entire course of calculus in hopes that maybe one day this will blow up into an amazing YouTube money-making scheme. In the meantime, I'm just going to educate a bunch of people on math. Calculus, so to speak. We're going to start with Chapter 1, which goes over limits and continuity. Now, before we talk about what you see on the page, well, let's actually just talk about what you see on the page. This is a tangent line. A tangent line is any line that represents a slope on any given point on a curve. So as you can see, I have this random curve here, f of x, boom, boom, it's blue, and I decided that I'm going to use that dot right there. I'm going to use that dot right there. And at that very moment, and imagine this is a roller coaster. You're going down, you're going back up. At that very moment when you're coming from going down in the bottom of the roller coaster, now you're making your way back up. At that very moment, your slope, your moment of incline is represented by that line right there. That's a tangent line. If I were to draw a tangent line here, maybe that tangent line would be a little bit flatter. Or if I were to draw it here, it would be negative. Okay, give or take. That's what a tangent line means. Okay, and we're going to talk about slopes of tangent lines a whole lot in this chapter. The first section that we're going to look at is limit. Okay, the limit is the behavior of a function as it approaches a given value. Imagine that there's something that you're trying to get, but you simply can't. I always go to the painting of Michelangelo and God in the Sistine Chapel. Michelangelo is reaching out his hand and God's finger is about to touch it, but it has not yet. Now we know in our minds that God probably touches Michelangelo's hand, but in the picture, he hasn't. But we know he will. We know he will at some point. Or maybe he'll just get really, really, really close. Because the picture makes it look like he's really, 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 really close. Well, the limit is where is my graph going to be at a specific time or at a specific point in the graph. We denote the limit by saying the limit as n approaches a. That's what we say. The limit as n approaches a of f of x. Now, if we look at this graph right here, if I were to say the limit as x, because there's my x value, approaches 2, let me see. Let's see what happens when I go to 2. When I go to 2, there's nothing. There's a hole there. If I were to ask you, what's f of 2? Well, f of 2 doesn't exist. Because if I were to plug in 2, if I were to go to 2 and follow that line right there, there's nothing there. Even though I know that this side of the line is basically going to 4 and that side of the curve is basically going to 4. I know it's basically 4, but it's not 4. This is God reaching out his hand. And this is Michelangelo reaching out his hand. And oh, there's just that space in between. And we know that they're going to touch. We know that they're going to touch, but it hasn't yet. That's what a limit is. The limit says, look, let's just say the answer is 4. That's it. So that's a graphical representation of a limit.
All right, we were all taught back in, when was it, Algebra 1, maybe even pre-algebra, that you can't have 0 be in the denominator. It's literally impossible to divide by 0. If you don't believe me, ask Siri what happens when you divide by 0. She'll tell you some terrible joke about Cookie Monster. I don't get it. But you can't divide by 0. So very many times when we see the limit as x approaches something, I can usually just plug in 1 and see what happens. Well, what happens when I plug in 1 here? I get 0 in the denominator because 1 times 1 times 1, 1 cubed, is 1. 1 minus 1 is 0. 0 in the denominator, that's no good. But limit does not necessarily mean, plug in 1. Limit means what is your graph doing as we get closer to 1? So this is what I'm going to do. If I wanted to graph this, like the graph of this guy looks something like this. But here at 1, we have a hole. So I can't, again, just plug in 1. I actually have to do some type of math here in a math class. I know. So I'm going to make a table. Okay? And I'm going to try 3 numbers on the left, 1, 2, 3 numbers on the right. In the middle, I have the number 1. I'm approaching the number 1. Okay, so what I'll do is I want to get really close to 1 without touching 1. So I'll do 0.9's pretty close to 1. How about 0.99? That's even closer to 1. And how about 0.999? I'm picking numbers that are, this is basically 1, but it's not. And so I'll do the same thing over here. I'll do 1.1, 1.01, 1.001. And again, that's basically 1, but it's not. And so I'm going to use my good old tried and true calculator to do a little bit of math. This calculator, by the way, is older than you. And I'm just going to type this in and plug it in. Let me see. X minus 1, well, in this case, X is 0.9. 0.9 minus 1 divided by 0.9 cubed minus 1. And I get negative 7.0. I think I typed out something funny, didn't I? It's saying I didn't. I did. I put plus 1 up there. Let's go back. Minus 1. All right. So it's telling me it's 0.36900. So 0.36900. Okay. Let's try it again. Parentheses, 0.99 minus 1, close parentheses, divided by, parentheses, 0.99 cubed minus 1, close parentheses, 0.3367. I'm running out of space there, so I'll just put that. Let's try it again. But let's do the 0.999. So, parentheses, 0.999 minus 1, close parentheses, divided by 0.999 cubed minus 1, close parentheses, 0.3337. Now let's do the same things with these guys. Again, if those of you who are like, what's going on? What's going on? I'm not allowed to plug in 1, but I'm allowed to plug in something that's really closer to 1. So if I even wanted to get closer, I can try 0.9999. But I won't. 1. Now this is the other side of 1, but something that's really close to 1. 0.001 minus 1, close parentheses, divided by 1.001 cubed minus 1, close parentheses, and I get 0.333000. 1.01, oh, I forgot to put it in parentheses, 1.01 minus 1 divided by 1.01 cubed minus 1. Did I put an 11 up there? I did. Surely that would change things. And don't call me Shirley. Airplane. 0.3300. Oh. How about 1.1? 1.1 minus 1 divided by 1.1 cubed minus 1. What did I do? Oh, I forgot parentheses. Second insert parentheses. 0.3021. All right. So, obviously, as I get closer to 1, I start out by being pretty close to 1 and closer to 1 and really close to 1. I get 0.333. And if I were to plug in a number even closer to 1, I'd probably get a few more 3s there. As I start all the way over here, I get a number that's close to 1. 1.1 is pretty close to 1, but 1.01 is really close to 1, and 1.001 is really, really close to 1, and I get 0.333. So this is telling me that if I were allowed to plug in 1, which I'm not allowed to do, but if I were allowed to plug in 1, I should get 0.333333333, which is about a third. Probably. I can't guarantee that, but you know what? If I got like 0.33, this actually was like 6 and 0.3330, kind of taking the difference and splitting the difference in the middle, I'm going to get 3s again. So the way I'll answer this is I will say the limit as x approaches 1 of x minus 1 over x cubed minus 1 is going to be a third. Now, more often than not, when I'm trying to find limits based off of not knowing how to do the math behind it, I'm more or less estimating or making some kind of guess, but a very accurate guess. And in this case, can't get much more accurate than that. All right, so let's take a look at another problem. We are being asked to find the limit as x approaches 0 of sine 3x over x by making a table. Well, once again, my predicament is I can't plug in 0. If I try plugging in 0, I don't care what happens up to the top here. If I try plugging in 0, I get 0 on the bottom. That's no good. So 0 is the problem. Let's make our chart. I have x values. I have f of x values. Let's put 0 right smack dab there in the middle. Plug in a number there, 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 plug in a number there. And if I can't plug in 0, then I can probably plug in something awfully close to it, like 0, 0, 1, 0, 1, and 0.1. Similarly, negative 0.001 and negative 0.01 and negative 0.1. So let me get my calculator out. Let's see what the graph of it looks like. Yeah. There it is. Just trying to get a nice little angle so you can actually see what's going on. So instead of typing all of this mess in, let me show you a little something. If I hit second calc and go to value, I can actually type these in if you're using a TI-84 or TI-83 plus like I am. X equals negative 0.1, enter. What do I get? 2.9552. Right? Second calc, negative 0.01. Oh, negative 0.01. 2.99955. Second calc, value, negative 0.001. Kind of crazy that I get 2.9999999. Didn't see that coming. And there's no way that something that looks like that. No way that something that looks like it's going up and then going down is going to have similar answers. I don't think it. There's no way. Second value. 0.001, enter. It's literally the same thing. Well, that's just a coinky dink. There's no way that'll happen again. There's no way that's going to be like 2.9995 or something. I don't know. The second calc value, 0.01. Interesting. Well, third time's a charm, am I right? Interesting. Now, it seems to me that I can't, let's keep in mind, I can't plug in 0, right? But if I plug just a little bit to the right of 0 and just a little bit to the left of 0, it looks like these guys are moving towards a specific number. And I'm no mathematician, but that specific number is probably 3. So we can say the limit as x approaches 0 of sine 3x over x is going to be 3. That's it. Now, in the pictures and the problems that we just did, it seemed as if much better. It seemed as if everything seemed to be going to the same spot. What if I gave you a crazy graph like this guy right here? What if I said, take that graph and find the limit as x approaches something from the right side? What would that look like? Well, I would denote that as this: the limit as x approaches a with a little positive symbol means you're coming from the right. So if instead of a, if I said the limit as x approaches 2 with the little plus sign, that means I'm going to walk along this curve right here and say, I'm going to 2, I'm going to 2, I'm going to 2. Here I am. There I am. That's what I want. My answer is 5. Okay, graphically. What if I want to switch this up and say, well, let's say I want to go to -4, but I want to approach it from the left side. So the limit as x approaches -4 from the left, I'm going to put a little negative on the top right as a superscript. So I'm coming in from the left. That's where I want to go. That's me coming in from the left. If I wanted to come in from the right, I would do this and say the limit as x approaches -4 positive, and I'd go here. So my answer to this problem, where I'm asking what's the limit as x approaches -4 from the left, the answer is 3. What's my limit as x approaches -4 from the right? My answer is -2. So we have differing answers. Those of you who saw Mean Girls, you probably know what's coming. Piecewise functions. No one likes them, but you have to deal with them. Just like my in-laws. I'm not kidding. They are monstrous, terrible people. I should have created my own coordinate plane for this, but I mean, I had one printed out, but it's too late. I'm gonna have mine go out to a bunch, making a coordinate plane. A piecewise function is basically you're graphing two functions onto the same coordinate plane, but they kind of split up at a specific point. And at this point, the place that they split up is at 1. Okay, I'm going to graph this guy in blue, in this dark blue, Jack's mannequin. The way I graph it is it tells me start at x is +1 and graph that equation. So when x is +1, that graph, let's see, what happens when I plug in 1? When I plug in 1, I get regular 1, but it doesn't count. My slope is 3, so I go up 1, 2, 3 over 1, up 1, 2, 3 over 1, and that's what my line will look like for that part. Those of you who are not good at piecewise functions, the internet's always there. But this guy, basically what you're saying is graph that when x is greater than 1. Don't include 1, though. So there's when x is 1. That's when x is 1. And usually the whole equation would look something like this. But since I only care about everything to the right of 1, I'm only going to graph that. I'll graph this magenta color for this. And I want to graph from everything to the left of -1. So if I were to plug in 1, I get 2. So I include 1 here. My slope is -1, so up 1, left 1, up 1, left 1, up 1, left 1, up 1, left 1, and I'm basically going to get that line. If I knew how to draw, I'd get that line. So my job in this problem is to find what my answer is as my limit approaches 1 from the right. So here I am going from the right. Obviously, I'm traveling down this blue path. And as I hit x is -1, I don't necessarily hit it. I don't necessarily get there, but boy, am I awfully close to regular 1. So my answer is going to be 1 because as I go from the right, I travel down that blue path and I hit 1. 1 is my answer. As I'm going from the left, though, I'm going down this pink slope, and I actually eventually do run into 2, right? 2. So when x is 1, I get 2 because it's like actually on 2. I am allowed to include it. How about another one? This is me making a coordinate plane. Very exciting. Very exciting. Where do I split here? I split at -2. So I care about stuff that's going on from the right side of -2. So when I when I plug in -2 here, and I want to go, do I have enough? Oh, I do. I'm fine. 1, 2, 3, 4, 5, 6, 7. All right. So I'm going to start at -2, which is here. If I plug in -2, I get -7 minus, or -2 minus 5, which is -7. So I start here. My slope is 1, so I go up 1, right 1, put a dot. Up 1, right 1, put a dot. Up 1, right 1, up 1, right 1. And eventually I get this line right here. I feel it should go through 5. On the left side, I have just regular old 2x. Just 2x. Plugging in -2 gives me -4. So, I'm at -2, -4. You know what? I did something dumb. I wasn't supposed to include that guy. Problem solved. All right, so if I'm at -2, to the left of it, I have a slope of 2. So this is going to go down to left 1, down to left 1. So this guy's going to look like that. Okay, straighten out my paper. What is the limit as x approaches -2 from the right? Well, here's coming from the right, all the way down here to -7. So my answer is -7. How about coming in from the left? -4. Now, some of you might be saying, listen, sir, I noticed that when you went from the left, you picked that equation, and when you the less than, and when you went in from the right, you picked that equation. You went from the right, the greater sign, greater than sign. Can't we just plug in -2 to that to get that answer? Yes. And can't we just plug in -2 to that to get that answer? Yes. But you're not supposed to know that yet. Shh. Okay, so remember how I mentioned Mean Girls? Not only is it a fine film, but in the movie, the climax is when Lindsay Lohan's character says the phrase, "The limit does not exist." Well, here we are. We've made it. Your favorite math subject and your favorite teen movie combined to make what we're about to see next. If I were to focus on this particular part of the graph, as I moved from the left, if I wanted to find out where the limit uh, of whatever this is called, f of x, what the limit as x approaches -4 is from the left, I would say coming from the left, it definitely actually goes and sits right there. So the answer would be 3. Coming from the right, it goes this way. Oh, it goes down there, and it doesn't actually make it to -2. But you know what? The limit is not supposed to necessarily make it to that number. It's supposed to get awfully close. And so the answer here will be -2. So from the left, it's 3. From the right, it's -2. What if I just asked you, what's the limit as x approaches -4, period? No from the left, no from the right. Well, the limit of a function only exists if the left side and the right side match up. If they don't match up and the left looks like this and the right looks like this, then the limit does not exist. So that's, in a roundabout way, that's what this is saying right here. This is saying the limit exists and exists at that exact point if the left side and the right side match. And wherever they match, that's what the limit will be if I ask you what the limit of that thing is. Not from the left, not from the right, period, with a T at the end. Now, so if I take a look at this guy and I ask you what's the limit as x approaches -4 here, from the left, it's an answer. From the right, it's an answer. But from regular old -4, the limit does not exist. And so we could say does not exist. Now, if I ask you the same question about the limit as x approaches -1, that's supposed to be an arrow to -1. Sorry. We do have an answer because there's actually a dot there. And so if there's a dot there, then the answer is obvious. The answer is going to be 4. But here, if I ask you, what's the limit as x approaches regular 4? Well, from the left, the answer's 2. From the right, the answer's 2. If I ask you to plug in 4, you don't have an answer because there's a hole there. But if I ask you what the limit is as x approaches 4, the answer will be 2. Okay, now keep in mind, the limit is telling us what's the answer basically going to be as we approach that area. We're not necessarily saying what is that dot on the graph, because here there is no dot on the graph. The limit is just basically saying if we have the hand of God, or wait, this is the hand of God, and if we have the hand of David, oh, we're so close, but we're not there. That's what limit means. And so the limit as x approaches 4 in this case is 2 because the left side is 2 and the right side is 2. And even though there's a gap there at 4, the limit means, well, we could basically say it's 2. All right, so we have ourselves another piecewise function. Okay, so let's have some fun and graph that. Make yourselves a nice little coordinate plan. One of these days I'm going to invest in a ruler. But in the meantime, I will not invest a ruler because as far as I'm concerned, Jesus is the only ruler that I care about. Okay. We have a 3-part piecewise function going on here. Okay. In purple, all the action, of course, happens at 2, as you can clearly see. In purple, I have -x plus 5. So at 2, I start at 3. So at 2, I start at 3. My slope is -1. So, Oh, and I did it again. I don't want the actual circle. I want a hole there. So, perfect. God is good. Okay. That was this guy. This guy, I have 2x minus 5. So if I were to plug in 2, I start at 2. If I were to plug in 2, I get 4 minus 5, which is -1. So I have a hole at -1. And my slope is 2, so I go up 1, 2 over 1, up 2 over 1, and basically that line happens. And what this fella is saying right here is at 2, when x is 2, I just have 1. So boom. So there's my actual dot. There's my filled in circle as opposed to what you see there in purple. So that's my piecewise function. Okay, that's my piecewise function. If I asked you, what happens if I take 2 and just flat out plug it in, no limits involved? Well, when x is 2, I get 1. There it is. So that's fair enough. As I approach 2 from the right side, this light blue line, cyan, if you will, I'm coming from the right, and from the right, I hit -1. From the left, I hit, what was that, 3. And if I ask you what's the limit as x approaches 2, the limit as x approaches 2 is, well, nothing. The limit as x approaches 2 does not exist. And the reason why it does not exist is the left limit, boom, and the right limit, boom, don't match up at the same spot. Again, from the previous slide, if the left limit and the right limit do not approach the same exact number, which according to these guys, they don't, then the limit does not exist. Even though we have a definite point here, the limit is, where is my graph approaching as I go to 2 or as x goes to 2? Well, from which direction? It's not clear. Because from the left direction, it goes here. From the right direction, it goes there. If I were to just plug in 2, I get an answer, but that's not what I'm asking. It's not what I'm asking. So let's take a look at an actual graph that's given to us. I don't have to deal with that piecewise nonsense. So here's our picture. We have a hole here, so I'm expecting some left to right side magic happening there. We have a split here at 1, so I'm expecting some does not exist action happening here. At 6, I have an answer, but I also have a hole and the left and the right side going to the same exact spot, so I'm expecting some fun to happen there, and that's where I begin this problem. If I'm looking at 6, if I plug in the x value of 6, I get 2 according to that right there. When I'm not giving you the limit, I'm just saying, hey, what happens on the graph at 6? Well, what happens at 6 is I get 2. No limits, no coming from the left and no coming from the right. If I just say find f of 6, I'm just saying what happens on the graph, and what happens on the graph is 2. Now that I have a limit, I'm asking you in this particular problem, what's going on from the right side? So from the right side, here I am from the right. I'm going, and I'm going to 5. So my answer here is 5. The f of x or the y value is 5. Coming from the left, I'm also going to 5. That's where my graph is headed. Remember, limit means where's my graph headed. So when it's asking what's the limit as x approaches regular 6, well, since the right side's going to 5 and the left side's going to 5, the limit does exist and the limit appears to be 5. Even though I have a dot at 2, the limit is telling me where your graph is going, not necessarily where the dot exists. Okay? When x is approaching 1, so that's where the other magic was happening. When x is approaching 1 from the left, I head to 4. And actually, I do hit 4 eventually, which is good news. But I go to 4. When it's going from the right, I hit -2. Well, I don't literally hit -2, but I'm heading towards -2. And when I ask you what the limit is as x approaches regular 1, well, from which direction, I don't know. So from the left, it's 4. From the right, it's -2. Oh, those are two different numbers. The limit does not exist. Since the left side and the right side don't match up, the limit does not exist. So let's take a look at infinite limits. Okay, because so far we've hit numbers and we hit them pretty nicely. Let's take a look at what it might look like graphically speaking. Let me get my light on. Let's graph this in our graphing calculators. If I have, and I'll graph it on the graphing calculator since my graphing calculator isn't showing up very well. I'll graph it in my graphing calculator first. It's very important that when you use a graphing calculator and you type it in, you include parentheses. So if I wanted to put 1 divided by, let me see, can you see that? That's better. What was it? X minus 5 in the denominator. Make sure you put x minus 5 in parentheses. Otherwise, your calculator won't understand what's going on. Plus 2. Okay, hit graph. So this is basically what our graph is doing. Okay, so there it is. Boom, 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 boom. As expected, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. TBH, to be honest. The other parts don't really matter because what's going on here is, as expected, everything blows up at 5. Why would everything blow up at 5? Because if I were to plug in 5, I get 0 in the denominator, and you can't have 0. I don't care about that plus 2. You get 0 in the denominator. That's bad news. So according to the calculator that I have, it looks like this guy goes through 2. Okay, it has this like nice little slope going on here. Where's 5? 1, 2, 3, 4, 5. It blows up at 5 and then reappears up here and goes like that. What we have here is what's called a vertical asymptote. When you have an explosion in your graph like we do here, and you have curves, whether it's a curve going down and coming back up or a curve going down and reappearing at the top, you have what's called a vertical asymptote. And that vertical asymptote happens at 5 right there. We also have a horizontal asymptote, and that looks like it's happening at 2, but that doesn't matter in this situation because I don't really care about horizontal asymptotes. I only care about vertical asymptotes. Say that fast. Right. What I'm being asked to do is find the limit as x approaches 5 from the right side. So 5 is where that explosion happened. So I'm coming from the right. Here I am coming from the right. I'm going way up here, and this is where 5 is. I never hit a number, and I can't hit a number because it wouldn't exist. But it appears to me, as I'm coming from the right side, my line is going way the heck up here. Well, where's that? That's positive infinity. So from the right side, my limit from the right side never approaches an actual number. It's not like in the previous cases where I would approach like 3. I'm approaching something that goes up there forever. So in this case, we would say that my limit as x is coming from 5 is going to positive infinity. My limit as x comes from the left side is going to do literally the opposite and go way down here to some type of negative infinity. So we would say the limit as x approaches 5 from the left side is going towards negative infinity. Now, what does that mean for my limit as x approaches 5? Well, does the left side and the right side match up? No, so the limit does not exist. So in the previous many problems, our limit approached a number or the limit simply did not exist. Well, here in these cases, when we have asymptotes, when things blow up like it did here, we're usually going to approach some type of infinity number if we have asymptotes, if we have an explosion like we did here. In previous problems where we saw the what's called the point of discontinuity, when we had an x value that made things blow up, before we would actually have a number. And you're wondering, well, why did we have that? Well, that's because we had x values up top, and you still have holes in your graph, but the x values up top kind of make simplification happen. Since I don't have an x up top here and I have just a regular number, we have this crazy explosion. So what we have here now is similar to the last problem, but what we had in the last problem is we had I forget what it was. What was it, x plus 5 on the bottom in the denominator? X minus 5 in the denominator. Now what we have is we have a perfect square trinomial. We have a squared going on in here. I wonder if that's going to make our graph look any different. I'll give you a hint. It will. So if I graph x plus 3 squared in my graphing calculator, which is what I'm doing now, and you can't see it. Okay, don't forget that parentheses in the denominator, otherwise it's going to not look good. That's 1 divided by x plus 3 squared, and hit the graph button. we see a vertical asymptote, but what it looks like is it's a roller coaster going from the left, taking a huge upturn up there, and it's happening at -3 because -3 is going to be the number that makes the bottom explode, and then it just comes right back down. So again, a very, very, very quick sketch of this graph, 1, 2, -3, 4, 5. It looks like this is going on. Going up at -3, coming down at -3. And so our vertical asymptote happens at -3. And again, if I were to draw a better picture, what we would see is these lines would just get awfully close to -3, but never touch -3 because -3 is a point of discontinuity, makes everything explode. It's bad news. So as we're approaching that -3 from the right side, here I am. I'm going from the right side. I'm going up. I'm going up. I'm getting closer to -3, closer to -3, closer to -3. I'm now off the paper. And where I'm heading is towards a positive infinity. So my limit as x approaches -3 from the right side, just like a previous problem, is going towards positive infinity. From the left side, as x approaches -3, I'm going up, I'm going up, I'm going up. That is also going towards positive infinity because it's not going towards a number, it's going towards the heavens, and in this case we get positive infinity. So unlike the last problem where we had things going in opposite directions, we have two infinities going in the same direction. So my limit as x approaches -3, since the left side's going to positive infinity and the right side's going to positive infinity, we could say that as x approaches -3, period, no direction necessary, we could say that that does exist. And that exists at infinity. Okay? So that, boys and girls, is the graphical representation of limits. One-sided limits, two-sided limits, piecewise functions and graphs. So much fun. Can barely contain my glee.